Greetings everybody, and today we're going to be calculating one crazy triple sum with three binomial coefficients in here. Now this is probably not the triple sum you saw in the thumbnail, like where are the three sigma signs? Well, I just collapsed everything down into one big sum just so it looks a bit cleaner and so on, but we're still ranging over these three indices. But yeah, this is something I found on the Math Stack Exchange while I was looking into integral representations for our binomial coefficients here. I have done a video on this in the past. I think the previous two videos on this topic, if I schedule everything correctly. But yeah, I'll link that video in the description as well as the post or the article to this problem in the description as well for your reference. Now, the solution to this problem is not entirely my own. It is based on someone who commented the solution to that post. I have made a couple of modifications just to make it a little bit more nicer, I guess. Well, in my opinion, a little bit more nicer. But yeah, all the relevant links and whatnot will be in the description. So what exactly is this sum? It's just three binomial coefficients multiplied together, and we're kind of multiplying these sums of pairs of the indices we're ranging over. Now, at first glance, you see the z down here, the integers, and you might say, well, I don't see any kind of decaying factor or anything, so probably this thing will blow up, but it actually doesn't. This thing is actually finite. I think you're only going to be summing over n plus 1 cubed terms, because with these binomial coefficients, if you kind of graph it out, if you graph, for example, n choose x, for instance, so if I graph n choose x and this is the x-axis, well, you're going to get a plot that looks something like this, kind of like a binomial distribution kind of. Now this would be, for example, n. So 0, your value would be 1. At n, it would be 1 as well. And after you go past n, anything past n, it is going to be 0. So x, it could literally be any integer. It could be negative as well, in which case it would still be 0. And if it's after n, it would be 0 as well. So in fact, you're just going, even though you're summing over infinitely many terms, well, only finitely many of them are going to be non-zero. And the reason why everything is 0 at all the integers greater than n or less than 0 is because of the gamma function. If you expand this out, this is n factorial over x factorial and minus x factorial. And for example, if x is negative and it's an integer, then the gamma function becomes infinity or blows up. So if you're dividing by infinity, then you're 0. And over here, if x is greater than n, well, the inside of this factorial also becomes negative. And if you look on the gamma function, well, it diverges, so it becomes 0. So that's why this sum over here actually converges. It's because we're only summing over finitely many non-zero terms. So with that out of the way, let's get into the solution. Also, I need to mention these guys as well. We will need to know these two facts. That's the contour integral representation of n choose k, which is this integral. I derived it in a previous video, as well as this fact over here. This is just the binomial expansion of 1 plus z to the n. You have n choose m and then z to the m. And then technically you would also have 1 raised to the, what would it be, n minus m or something, but that's just 1, so I left it off. So we will need those two in the solution. So what is, I guess, the tactic to solve this sum? What we're going to be doing is we're going to be breaking this up into, I guess, smaller sums, and then turning these binomial coefficients into these contour integrals. But we're still going to get binomial coefficients flying around everywhere, unfortunately. And the way to resolve those is to use the second fact. We're going to try to force some kinds of z raised to some power, and then we're still going to have these sums from various places, and then we're going to use these leftover binomial coefficients, you could say, to turn all this back into 1 plus z to the n. And this actually nicely matches up with what we have in the contour integral, so more nice simplifications will happen there as well. So that's the general idea of the solution. Now, I think I've talked for way too long. Let's get some writing down. So what's the first thing we can do? Well, we can split up the sum a little bit, because notice these last two factors, they only have L's in them. So we can kind of factor a sum with only L's. First of all, I'll call this sum maybe capital S. And we're going to, as I said before, factor out a sum with L's. We're going to kind of factor it to the backside. So first of all, we still have the sum with j and k running through the integers of n, choose j plus k. And then now we're going to have the sum over L of n, choose k plus L. And then we have n, j plus L. Okay, so now what we're going to do is we're going to extract out this second sum, or this inner sum here, and we're going to be turning one of these binomial coefficients into a contour integral. Let's just call this sum over here, let's just call it, I guess, t. So what is t? T is going to be the sum over our L's, and then we have n choose k plus L, and then n choose. Now instead of j plus L over here, I'm going to use the fact that n choose k is the exact same thing as n choose n minus k. So here we're going to have n minus j minus L. Now the reason why we do this is because we're going to be turning this binomial coefficient into a contour integral, and actually want to have a minus j and a minus L in the denominator, because that's actually how we're going to produce this expansion over here for the binomial expansion. So this is a good thing to do. So let's see what this looks like once we turn everything into a contour integral. I'm going to leave this binomial coefficient. I'm only going to work on this guy. So we're going to have a factor of 1 over 2 pi I, and then sum of n, choose k plus L. Now we're going to have the contour integral over some curve C, or suitable curve C, of, now how do we turn this into a contour integral? Well, we have 1 plus a z raised to the top number, which is n, and divided by z, but raised to the bottom number, which is n minus j minus L, and then we have to remember to add a 1 to it, and then dz. Now, okay, so now what I'm going to do is I'm going to move this whole entire sum into the integral, including this factor, or this binomial coefficient, because it's independent of z. Now notice technically this would just be a finite sum, so we have no problems putting it into the integral. So this becomes 1 over 2 pi I, and then we have the contour integral over c of, we have 1 plus a z to the n minus j minus L plus 1, and then we have the sum over L of n, k plus L, and then a dz. So notice, what do we have? We have a sum of a binomial coefficients over here. Now we want to try to use this second fact somehow. The only thing we're missing is a z raised to some power. In particular, what power? Well, the power must match the index. In this case, it would be m, but over here, it must be exactly L. So we're after some kind of a z to the L right in over here, and I can actually take that from z to the minus L in the denominator. That's why I wanted a negative power here, so I can flip it up to the numerator. If I haven't done that, then I would have 1 over z to the L, which is a bit awkward to do. But yeah, let's do that. So we have 1 over 2 pi I, contour integral over c of 1 plus a z to the n minus j, and then we take that L, so we only have a plus 1 left. We have the sum running over LL of n, choose k plus L, and then we borrowed that z to the L, so let's stick that over here, and then we have a dz. So this sum here is kind of like its own little thing. Okay, so this is looking good. The only problem is this k plus L in here. I don't want the k plus L, I only want an L. So how do we fix that? Well, on this next equal sign, we're going to do a little bit of a shift in our index, because notice L is running through the integers. So if we shift it by something, L still runs through the integers. What I'm going to do is I'm going to take k plus L, and then I'm going to replace that with just L, which is what I wanted. But what happens to this lonely L up here? Well, L is just going to be mapped to, well, if we subtract k on both sides, it's going to become L minus k. So we're just shifting our index a little bit. So now we have 1 over 2 pi I, contour integral over c of 1 plus a z raised to the n, and then we have z to the n minus j plus 1. We have the sum. L still runs through the integers because we're just doing a little shift. Now we have n, choose k plus l, but that turns into an l, times a z to the l, but l now becomes l minus k. So we can write this as a z to the l over z to the k. And now you might say, well, what's happening over here with this z to the k now? Well, let's not worry about it too much because this sum only depends on l. So this z to the k, we can just move it back onto the outside. So let's do that. So z to the l still survives, but now we have z to the k down here as well as an extra factor, but let's just add on the power of k to the ends here. Okay, and now notice this guy, this is quite nice. We only want L to run from 0 to n though, but it doesn't matter if we run through the integers because any L's that are less than 0 or greater than n would just vanish. So this sum would be kind of equivalent to this sum. So we can simplify things a little bit. So this whole entire guy, this becomes 1 plus z, but raised to, well, the top number here is n, which is quite nice. That's what the sum simplifies down to. And notice we have this factor, which is the same as this factor, so we can rewrite this as 1 over 2 pi I, contour integral over c of 1 plus a z, but not to the n, we have 2n here, and then this whole thing is divided by z to the n minus j, let's write a plus k, and then a plus 1 to finish off, and then we have a dz. So what did we just find over here? We found that the t, this sum over L, just evaluates to this contour integral expression. Now we could just turn this back into the binomial coefficient, but there's actually no need to at the moment. And we can substitute this expression back into our t over here and actually kind of repeat the whole process, but I think it's for j next. So we're going to try to force another one of these binomial expansions. So what I'm going to do, I'm going to erase everything and I'm going to replace this part over here with this sum. So this is what we have now so far. Now we're going to kind of repeat the whole thing, but we're going to bring another sum into this contour integral. Now, which sum should we bring in is the next question. Well, remember from before, we wanted to generate this z raised to some power, but we borrowed those z's from the denominator here. So which one should we take next as the sum to bring in? Well, it makes sense to take in the sum that's over j, because this is z to the minus j in the denominator. We can flip it up to become z to the positive j in the numerator. So now let's bring in the sum over j. So this is the sum k over z, which still is outside. Now let's actually bring that 1 over 2 pi I factor onto the outside first, just to get that out of the way. So yeah, we still have the sum over k that's still hanging around on the outside. Now we have the contour integral we have 1 plus z raised to the 2n over z to the n. Now I'm going to use that minus j, so let's ignore it for now. So n and then plus k plus 1. Now we have the sum. Now we put in the sum over j, and we also have to pull in this binomial coefficient, which is n j plus k. Now I use that z to the minus j, I'm going to flip it up over here. So this becomes a z to the positive j and then a dz. So this sum is kind of its one thing in there. Now again, we don't like a j plus k. I'm going to shift the index a little bit. I don't think I can fit it there, so I'll do it down here. So we want j plus k to turn into just j. And what happens to the j up here? Well, j, that's just going to turn into j minus k. Okay, so now we have 1 over 2 pi I, sum over k, contour integral over c, 1 plus z to the 2n over z to the n plus k plus 1. Now we have the sum, j over the integers, n, j plus k becomes just a j, and then we have a z to the j, which becomes a z to the j divided by z to the k. So z to the j I'm going to keep, and the division by z to the k over here, I'm going to bring that and multiply into this z, but notice we have a plus k and another plus k on the denominator, so this actually just becomes n plus 2k, and then we have a plus 1. That's what we're going to get, and also dz. Now this sum over here, we can compare it to what we had up here. This whole thing, that's just going to collapse down into 1 plus z, but raised to the nth power. Okay, so now this is equal to 1 over 2 pi I. We have the sum, k over the integers, contour integral over c of 1 plus a z raised to, this is an n and then a plus 2n, that's a 3n, divided by z to the n plus 2k, and then we have a plus 1 and dz. Okay, so this is really quite nice over here, because now while we have a sum, I don't think we can put the sum into the integral anymore. That doesn't really make sense to do because we don't have any more binomial coefficients flying around. Let's turn this contour integral, along with this factor of 1 over 2 pi I, back into a binomial coefficient. So now we have the sum, k along the integers. Now, what does this turn into? Well, it's going to be a binomial coefficient. What do we have on top? Well, the number here, which is just a 3n. And then we also have the number on the bottom, excluding this one. So that's going to be n, and then plus 2k. So that's pretty nice. This triple sum just simplifies down to just this small sum of some random binomial coefficients. Now, how do we finish off from here? What I'm going to do is I'm going to erase what we have up over here just so we have a little bit more space to work. So this is equal to the sum, k over the integers of 3n, choose n plus 2k. Okay, so notice one thing, what's going on? Notice on this bottom slot, we have n plus something, but that something over there, namely that 2k, is only ranging over the positive integers. So we can actually write this in another way. This is a little trick that's pretty cool. So if we were to write this as a sum and then a k over the integers of just 3n, but then we have an n plus k, we only want this term to survive when k is even. In other words, we want some other factor here which kind of turns on when k is even and turns off when k is odd. So you might think of some oscillating thing like sine or cosine or something like that. We could use this following factor, which is 1 plus minus 1 to the k divided by 2. So this is a special factor which kind of turns on and off depending on if k is even or not. So if k is even, then we get 1 plus 1 and then over 2, which is 1. But if k is odd, then this minus 1 to an odd power is still negative 1, so we get 0 overall. So this is kind of like a little indicator thing. So now what we can do is bring out this half factor. So this is a half, and then now we have the sum, k over the integers, and we can distribute across this sum. So now we have 3n, choose n plus k, and then we have a plus another half, sum k over the integers. Now we also have to have this factor of minus 1 to the k. So we're going to have 3n n plus k, and then we also multiply by minus 1 raised to the k. Okay, so this is what we have so far. Now one kind of final simplification I want to make, I'm going to again shift the index. So I want this n plus k just to turn back into a k. The k is over the integers, so it doesn't matter if we shift it. So I want n plus k to be mapped to just k. So whenever I see a k, I'm going to map that to, well, that's going to be k minus n. Okay, so let's see what this gives us. We have 1/2 sum k over the integers of 3n, and then this just turns into a k, so nothing fancy happens on this first sum. Now we have a plus 1/2, and then we have a k over the integers once again. Again, we have a 3n, choose k, but now this minus 1 to the k, that's going to become a minus 1 to the k minus n. But notice we can split up, I guess, this power and bring a minus 1 to the minus n out to the front, or that's the same thing as minus 1 to the n, because that's independent of k. And now take a look at what we have. We have a sum of binomial coefficients and a sum of again, a binomial coefficient, but it's kind of alternating. Now he wants to turn this into an expression that we can kind of recognize. Maybe you see a sum of binomial coefficients somewhere, namely over here. All we need is, for example, a z raised to some power, but we don't quite have that. So what I'll do over here is I'll write this as the sum k over the integers. We still have 3 and choose k, but I'm going to kind of write it as 1 to the, I think it would be k, and then 1 to the 3n minus k. So hopefully you guys see where this is going. And then we have plus 1/2 minus 1 to the n, sum k over the integers, 3n choose k. Now this minus 1 to the k, that's good to have, but then we're kind of missing something, namely we're missing a 1 raised to the 3n minus k. So notice both of these over here, those are binomial expansions, so we can collapse them all together. So this is a half. This guy over here, this just becomes, we have 1 plus 1, but this is raised to the 3n power, and then we have plus a half minus 1 to the n, but now we have, what do we have? This is going to give us, what we have, a minus 1 and then plus 1, but this is raised to, again, the 3n power. Minus 1 plus 1, that's just a 0, so this whole entire second term actually vanishes, assuming n is a natural number. I actually forgot to mention that at the very start. My bad. N is a natural number. And then how about this first sum? Well, that just becomes 2 raised to the 3n, but we have this half out here. So what this becomes in the very end is 2 to the 3n, and then minus 1 because of this half. Now this should be the final answer if you assume n is a natural number, which means it doesn't include 0. I'm pretty sure if you want n to be equal to 0, you also have to add on some kind of Kronecker delta term. I think it's something like Kronecker delta n 0 times a half or something like that. Because over on this line, if n is equal to 0, then this would just be a 1. This whole entire sum would evaluate to 1, and then n is 0, so we ignore this. So yeah, we would get an extra 1/2 times 1, which is the half. But assuming n is a natural number, then we don't really need this fancy Kronecker delta stuff, and we can just take this 2 to the 3n minus 1 as our answer. So that's a pretty simple and nice answer for such a complicated mess up here. But yeah, this was quite a fun sum to work through actually. Some nice tricks involved and whatnot. So I hope you guys enjoyed this one as much as I did. And yeah, if you guys have any problems you want to suggest for me to do on this channel, feel free to email me. You can find my email in the about section. But yeah, that's all for today. Up until the next one, hope you guys have a wonderful day, and I will see everyone later. Bye bye.